So I'm going to talk about the speech intelligibility work, or specifically the speech intelligibility metering that we've been working on as part of the project. So there's well-established problems with dialogue not always being intelligible on television, for example, and there's a variety of reasons for this. We didn't really tackle the top one, which is about actors not actually delivering and mumbling. We actually were more concerned with the bottom three causes of problems. That's when you have maybe background music that's too loud, so the balance is wrong, or you're in the kitchen and you're watching the telly and then someone turns the kettle on, so there's ambient noise that causes you problems. Or it could be when you're listening to a modern television, which unfortunately is very thin and has very poor quality loudspeakers on them. And S3A has looked at all those kind of issues in different ways. So we've talked this morning quite a lot about object-based audio, and that has real potential for improving intelligibility because you can tailor the mix to reproduction equipment and you can personalize the mix to the listener. Because you have all the separate sounds, you have the dialogue and you have the other sounds separately delivered with metadata, at the consumer end, at the television, you can personalize that mix to whatever situation that you want. And essentially we're talking about processing either the dialogue or the background to improve intelligibility. So for the dialogue sound, it's speech, you could, for example, you could apply some compression or you could make it a bit louder. For background sounds, you might take a background piece of music and change the frequency response. So you might take out some of the middle frequencies, giving you space for the dialogue to be intelligible. So there's a variety of things that we can do and play around with in object-based audio, and we have. I'll leave the bottom one for Ben to introduce in the next talk. So a kind of typical adaptation process is shown in this diagram here, where on the top left-hand corner we have the background sounds, we have the dialogue, and we have the metadata. It goes to the renderer, and then we get a mixed audio scene that goes out to the loudspeakers. What we also have is we have a speech intelligibility meter, which is working off the audio mix and also the dry speech to estimate the speech intelligibility metric at the bottom. And if that speech intelligibility metric drops below a certain threshold, then we'll take some process. As indicated, what we're doing is we're doing this through adapting the metadata. So we change the metadata and improve the scene for its intelligibility. So here's just a picture of it actually in use. So we've actually got a background and speech signals, which on the left hand of the three columns isn't being adapted, and on the right hand and the middle one is being adapted. And this weird acronym DWGP is one of our intelligibility measures. So we're asking for a bit more intelligibility in the middle and a lot more intelligibility at the end. If you look down at the bottom slide, what you'll see there is you'll see the estimated intelligibility on the y-axis. The blue is the original, and you'll see the two thresholds we're working at as the dotted lines. So we want to make sure in the middle section that the actual estimated intelligibility is above the first dotted line, and you'll see in the red when we have the adaptation on, we get into that intelligibility range. And the right-hand side, we ask for intelligibility to be above 0.8, and you can see that we adapt further. In this particular demonstration, it was just gain. It's the relative balance of the foreground and the background that is being changed. So to enable this work, we had to have a speech intelligibility measure. This is some references to the one we used that Jan developed originally for his PhD and made binaural for our work. And so this is a score of word scores correct versus another metric along the bottom. And you can see we get nice correlations between people scoring in perceptual tests and our metric. But you'll notice there's two sets of lines. One of those is speech-shaped noise, that's the black ones, and the white ones are competing speech, because this speech intelligibility meter doesn't do everything. It doesn't deal with informational masking, for example. So there's still work to be done on intelligibility measures. And the other issue that we have around using this intelligibility metric is it's rather slow. So what we've been working on recently is actually speeding it up. And we've used what's called a distillation process for machine learning, which is where you actually just train a neural network, in this case, to mimic what the meter is doing much more rapidly. So this is quite a lightweight neural network. It's not deep learning. It's very shallow. And what you're seeing as a graph is the estimation of the neural network on the vertical axis, and the ground truth is the real intelligibility metric, and you can see we can get nice correlation. And we're purely doing this for real-time operation. We'd use the old meter, there's no problem with that, but this allows us to do real-time adaptation. And that's where we're going for next. So what we're currently producing is a VST plugin to allow people in a door to actually monitor the speech intelligibility. That's nearly ready and to go. And we're also going to release open source code. We already have for the full model, but for the neural network code as well, so that people can use it to monitor speech intelligibility. Those are up and coming things, hopefully to be done by the end of the project.